In the last video, we took a look at this properties of the sampling distribution of p-hats box that we have here. And much like we saw in the section on the sampling distribution for X bar, this box is not something that we're going to have to memorize and be able to kind of regurgitate at any moment, because actually this is all summarized in the formula sheet for this section. If I take a look at the formula sheet, I can see that in this last column, everything from that box has been written down here. I have my random variable of p hat. I know it will have a normal distribution as long as both of these checks are met. Then I'll have formulas here for how I would find the average p hat and the standard deviation of p hats. The average of the p hats is given by just the value of p itself, and the standard deviation is calculated using this messy square root formula. And then, since I know that I'm working with the normal distribution, it would make a lot of sense that my calculator commands are still going to be normal CDF to calculate probabilities, and inverse normal, in this case, to calculate possible values of p hats that might occur on a number line. Now, when I think about this column of p hat, it's important to remember that we're thinking of asking questions that are going to get at measuring percentages of a sample. That's what this column is all about. I'm curious about percentages of a sample. And so notice that this is different than what we looked at in the X bar column, where we talked about the average of a particular sample. So you can see that we've gone through on our formula sheet and labeled pretty much all of our columns here with the idea of what each of these specific distributions is used for. And understanding these is super important, because as I read through questions, I have to consistently try to figure out, well, what sort of question am I being asked? And so for this section, it's important to remember that p hat is the variable that we use when we're interested in measuring the percentage of a sample that might come out a certain way. Now what we're going to do here is take a look and see how this stuff applies as we look at something like example number 2. All right, let's take a look at what we have. Suppose that a company claims that 5% of all of their products are defective. Okay, before I even go any further, I should be able to immediately highlight that when we're talking about this 5% here, 5% of all the products made by this company are defective, that's giving me a value of P. It's kind of like how in the last video we said there were 25% of all cards in the deck were hearts. So this is an overall population percentage. Okay, so a company claims that 5% of their products are defective. Now we're going to go ahead and do a random sample of 220 products. We're going to test them, and we're going to calculate what percentage of those, just though that small group of 220 is defective. Now we're going to assume here that this company produces, say, hundreds of thousands of products. Okay, so we're only grabbing a tiny, tiny little portion here. So what we want to do is start right at the top of the formula sheet. We want to define a random variable, state its distribution, and ultimately its parameters. So let's see. We can see here that if we want to grab a sample of products and we want to calculate the percentage that are defective, that is exactly what the variable p hat stands for. It's the percentage of a sample. So I'm going to say, how about we let p hat represent the percentage of the 220 items that are defective. I don't know what this number is going to be, but I can say that p hat is going to be the symbol that stands for it. Okay, so a lot of different p hats could come out of this. If I was to run this sample with my 220 objects and you were to do it with a different 220 objects, we may not get the same percentage back. So again, some p hats are more likely and some are less likely. But what distribution do they have? Well, according to the formula sheet, we know that p hat has a normal distribution, and we know that because, or when, we actually do these two checks. So I'm going to tackle both of these checks, and when I'm thinking about how exactly I'm going to do that, I tend to think about these checks as having a question mark occurring above the inequality sign in each of these. And so I'm really trying to figure out that once I plug in all the numbers on the left and the right, will these resulting inequalities be true? That's what I need to see. So let's take a look and see what we have for this question.
So my first check says that n times p times 1 minus p, is that actually greater than or equal to 10? Well, let's compute it. I can see here that my value of n is 220. That's how many items I'm selecting. My value of p is 5%, or 0.05. So of course, if 5% is p, then 1 minus that 5% would be 95%. Now, if I was to go to a calculator and actually crunch this value out, I could see that the number that I would get back is actually the value of 10.54. And so 45. And so our question is this greater than or equal to 10? And well, very, very clearly we can go yes. Now, this isn't the only check I have to confirm. I need to do a second one. So my second check here is 20 times little n needs to be less than or equal to big N. Remember, big N would stand for the population size. So I'm going to go here and say, well, let's see, 20 times my little n is 220. So that would give me a total value of 4,400. And I'm curious, is that less than or equal to capital M? So again, we took a sample of 220 products. And we know that the company produces hundreds of thousands of products. So I don't know exactly how many. I don't know what capital N is, but I know it's in the hundreds of thousands. So is 4,400 less than a number that's in the hundreds of thousands? Yes, absolutely. So I can check this off. So now I know that p hat does indeed have a normal distribution. And the last thing is state the parameters. So I'm going to state the mean for p hat, and I'll state the standard deviation.
So, going back to the formula sheet, we see that the mean for p hat is just p.
My value of p is 5%, so this value here is 5%.
To get my standard deviation, I have to set up this big square root formula where I have p times a 1 minus p divided by an n, and all of that underneath this radical.
So I'm going to end up with p, 1 minus p, remember, is just 95%, and then over 220. And again, I'm going to put kind of the same disclaimer that we did back in the video on X bars, where I'm going to say, let's always make sure that we don't round this value. I don't want to hand a rounded value to the calculator. I'm just going to give the calculator exactly this value to work with. So let's go ahead and try to take this into something like part B. Compute the probability that I would actually go out and find less than 4% of the items in my sample being defective. So if I think about what this means pictorially, I can say, all right, there's a lot of different p hats that I could get. I know that they fall into a normal distribution. I know the most common or the average p hat to get is 5%. And I know that there's a standard deviation of p hats that's given by this value. I don't really know what it is, but I don't want to write out a rounded off version of it. So I'm just going to leave it just like that. Now I'm interested in finding what are the chances that I get less than 4%. So 4% would be like over here on the number line, and I want to go less than it. So I want to find that shaded space. What's the likelihood that the p hat I get is 4% or lower? Well, since I'm looking for a probability, I would say I want the probability of p hat being less than 0.04, and I know I can calculate that with a normal CDF. So it's a normal CDF that goes from -1 E99 all the way up to 0.04, and then I use my mean, and I type in this entire messy standard deviation, the whole thing. I'm going to type all of it in. So this is over 220. So when I have all of that in, then I could go to the calculator and actually crunch this. So I'm going to go ahead and do it right now just to see what I would end up with. Okay, so I'm going to click on second, vars, normal CDF. I'm going to do -1 E99. I'm going to go to 0.04. Average is 0.05. And notice here I'm going to have to do square root 0.05 times 0.95 divided by 220. I paste that, hit enter, and I get a value of 0.2481. Okay, so I get 0.2481. Great, so this is it. Hopefully this feels unbelievably similar to everything we did with normal distributions in the past.